Good day. Last time out, we talked about how you can use RCC11 Element Design Spreadsheet program to design slabs. So today we'll look at how we can apply it to beams. To design beams, you click on the tab at the bottom here, which says rectangular beam. And so this is specifically for designing rectangular beams. There are two main sections here. We have the input section and the output section. The input section is where you enter your data, and the output section shows the results. Now, as it says, the operating instruction, enter data in blue cells only. So this is where you put in your beam data, and this is where you will get the answers. Now, in the answers, you can see the workings. For instance, how the effective depth is calculated, the K, the Z, and then the area calculated, the area of steel calculated, and the area of steel provided. You could see how it's checking for excessive deflection, and then you will get the status of your results. So if deflection is okay, it will show you. If it's not, it will also show you. Also, looking at the expanded section here, the beam can be designed as simply supported span, continuous span, cantilever. Now, the simply supported span is assumed that you are designing the beam one by one. In a continuous span, you are designing the beam as part of a set of beams that are identical in span, side by side, and then also a cantilever if the beam has no support at the end. Let's keep it at simply supported span. Taking a closer look at the input section, next to location, you can input the name of the beam, then design moment. Now, prior to using this spreadsheet program for beam design, you will have obtained your design moment for the beam. So this is design moment, which in this case is 300 kilonewton meter, and redistribution factor, which you can leave as 1. The span means the length of the beam, the height, sectional height of the beam, which is 600 mm, the sectional breadth of the beam, which is 300 mm. Now, the tension reinforcement, which in this case is 20 mm, the compression reinforcement, which is 12 mm. We have FCU, which is 30 Newton per millimeter square. That's the strength for concrete. We have Fy, which is the strength for steel, which is 460 Newton per millimeter square. We have the factor of safety for concrete, which is 1.5, and the factor of safety for steel, which is 1.05. Here we have the compression cover, 35 mm, tensions cover, 35 mm, side cover, 35 mm. Now, all these values, you can change them. So, for instance, your design moment may be 150, your span may be 4,500 millimeters, your height maybe 550, the sectional height of the beam, maybe 550, and so on. So all these are subject to change. Now, looking at the output, we have the results. This D here is effective depth. The K here, this is the moment capacity. This K with a dot on top here is the moment capacity, which is 0.156. The calculated K is 0.108. And if you look at it, since the calculated K is less than 0.156, compression reinforcement in this case is not required, but you still have to include it. Now let's go to the right screen here. You can see this AS represents compression reinforcement required 0, but then in practice you still provide nominal compression steel, which is 2T12 compression steel. This is Z. These are calculations how they arrive at the required area of steel for the tension. So based on this calculation, this K here, because it's less than 0.156, there is no compression reinforcement. And it means that this K here is more than 0.156, there will be compression reinforcement. For now, we only have tension reinforcement, which in this case is 1,434 mm, and then the area of steel provided is 5T20 tension steel, which is 1,571 millimeters squared. Now, the design also checks for deflection, and we have the permissible L over D, which is 19.737, and the actual L over D, which is 9. So this checks for deflection, and in this case, deflection is satisfied. In the right part of here, you can actually check further details concerning the design. For instance, the program also checks for maximum spacing of the steel reinforcement. So sometimes the steel can fail in spacing requirements. So it checks for spacing requirements as well as deflection. Okay, let's say I increase this moment to say 600 and I click enter. Now something happens. It tells me that compression steel is required. Now, to show you that this thing checks for spacing of tension steel as well, let's assume that in the sectional depth of the beam, I change it to 230. Once I click on it, it tells me the section fails on tension spacing. So in this case, you can see that although the design is passed for steel reinforcement and deflection, but it fails in the spacing of the steel bars, the tension steel bars as required by code. So let's go back to our 300. So you can use this spreadsheet program to economize your design, quickly ask questions by changing the input parameters, and it will help speed up your beam design. So as I said earlier, you can design it as a simply supported span, continuous span, cantilever, and so on. Now, once you are done, you can easily print out your results. So you do that by going to File and then Print. So here you can see what you're about to print out. So this is a preview of what you are to print. You can see your input values and then the results. So once you print to PDF, it's okay. You don't need to, print it out physically, and then you can save it as a file. So now let's go back. So generally, this is how you can use RCC11 Element Design for beam design. Now, if you want to gain a better understanding, or you are finding this thing hard to grab, AI can actually be of help. So what you do is you will take a screenshot of the relevant area of the spreadsheet program. For instance, I'm going to take a screenshot and then I will ask Google Gemini AI to explain in a diagram. So let's do that. There are several ways you can take screenshots. So in this case, I'm taking this part here. I'll save it, say beam design A. So I'll go to Google Gemini, gemini.google.com, and then I'll click on this plus sign to upload that picture. So I'm going to go to where I saved that picture. Now this is the picture of the spreadsheet. So I will now say explain in a diagram. You can actually experiment with different prompts, but this is the prompt I'm using for now. So I will hit enter. Now Google Gemini tries to interpret the picture. Let me now download the full size of the picture and let's look at it. Let's compare. One thing I would like to let you know, when you are using Google Gemini to help you to interpret your spreadsheet program, Google Gemini may not get it 100%. So which means that you need to check it very, very well. You need to check very well and note any errors. But Google Gemini or any AI tool that you use will go a long way in helping you to understand the spreadsheet program and how it works. While it tries to output the same design that we have here, let's take a look at this section. You can better understand. You can see the height. The section height is 600. You can see it here. And then the section breadth is 300, which is here, which is correct. So it gives us a visual representation of what is here. This is how you can use Gemini AI to better understand what the spreadsheet program is all about. In my next tutorial, we'll look at how to apply it to a T-beam or L-beam. In reality, beams are usually designed as particularly continuous beams are designed as T-beam and L-beam, and so that will come in the next tutorial. Thanks for watching this video. The link to this spreadsheet program will be provided in the video's description. Like and subscribe for more civil engineering tutorials.